Hi everyone. In the first video, the proofs did not record with volume. So I have the proofs over here because I wrote them up before, but I'm going to go through how to get this proof again so that way you can hear it with sound. So the first thing I'm going to do is I'm going to mark my diagram with the given information. So I know that I'm working with a parallelogram here from the given information. But I know a lot of things about parallelograms. I know that opposite sides are congruent, opposite sides are parallel, opposite angles are congruent. I know a lot of things. So rather than mark everything into my diagram, I'm going to hold off a bit until I mark my other given information and take a look at my proof statement. So that way I don't make my diagram super filled up with things that might be unnecessary, which might end up confusing me about what's important to actually prove what I need to prove and what's important to actually be in my proof. So moving on to the next given, it says that BE is perpendicular to CD. So here's BE, and it's perpendicular to CD. So I know that right angles are formed. There's also a right angle over here. It also tells us that DF and BFC are perpendicular. So I know that means right angles are formed. And there's also a right angle over here. The last given tells us that CE is congruent to CF. So here's CE and here's CF. My goal is to prove that ABCD is a rhombus. We already know it's a parallelogram from the givens. We just need to prove a property of a rhombus to show that it's also a rhombus. Now, we have a couple of properties of rhombuses. We have consecutive sides are congruent, which means all the sides are congruent, that it's equilateral. We have diagonals are perpendicular. Diagonals bisect the angles. But thinking about it, there are no diagonals here in this diagram. Looking at the diagram, diagonals go from one endpoint to the opposite endpoint. So the diagonals here would be BD and AC, but those aren't here. There are no diagonals. So I'm not going to be using the properties of diagonals to prove that I have a rhombus. So that leaves me with just one special property of a rhombus. If I can show that any two consecutive sides, any two sides next to each other are congruent, then I'll have proved that my parallelogram is also a rhombus. So I already, from my givens, have information about part of side BC. I have about CF right over here. And I already have information about part of side DC. I have information about CE over here. So what I'm going to do is I'm going to see if I can get more information about BC and DC. Because if I can prove BC congruent to DC, then I'll know I have a rhombus because consecutive sides will be congruent to each other. Now, a lot of people were trying to use addition postulate. They were trying to do FC plus BF to make BC and CE plus ED to make CD. Sounds reasonable. The only issue is that you don't know that BF and DE are congruent to add them. Remember, anytime you're using addition postulate or subtraction, you're starting with congruent and adding congruent so that your sum stays congruent. So even though I'm starting with two congruent pieces, I can't add on two pieces to those congruent pieces unless those two pieces are in fact also congruent. Otherwise, I don't know if BC and CD are going to be congruent if I'm adding on two not congruent pieces. So what I'm going to do, since the addition postulate that I just described is not valid here, is not going to work, I'm going to think about what smaller shapes I see inside this parallelogram. And I see a bunch of triangles. Now, taking a look at the small triangles here, one hint that I'm not going to be focusing on these triangles is that this point over here doesn't have a name. And on Regents questions, if a point is not named, it's probably because you don't need that point. You could give it your own name, but you don't need it. Thinking about if I was to focus on these two small triangles, the information that I would have to work with, I have right angles here and here. I just want to draw this in to make it more visible to you guys. I have vertical angles, but that's it. These are not diagonals, so I don't know anything about BE and FD. All I would have are two angles, and that doesn't prove triangles congruent. So I don't have enough information to focus on the two smaller triangles. So I'm going to think bigger. Just like the hint says, I'm going to look out for overlapping triangles, and I'm going to remember my strategies for working with them. So our two strategies for working with overlapping triangles are to draw them separately and to use color. So I'm going to do both. I've already been using some color, so I'm going to highlight my overlapping triangles. And when I'm highlighting my overlapping triangles, another hint that I wasn't going to use the small triangles is that if my goal is to end up with BC congruent to CD, I want to choose triangles that have those as sides, because that way, after I prove the triangle's congruent, I'll be able to use CPCTC to get information about those sides that I actually want to prove that I have a rhombus. So this bigger triangle over here has BC as a side. And CD's over here, it's a side of this triangle. So I'm going to draw the two triangles separately right over here. So I'm going to just face them the same ways that they're facing. So that's B, C, E. And then we have this triangle, that's F, C, D. And that's why in my diagram, I only put these two right angles in, because those were in the bigger triangles. This angle is angle CFD. CFD, it's this angle right here. I'm going to put that in. This angle is angle CEB. CEB, that's this angle right here. So already we have a right angle in each of the two overlapping triangles. From our givens, as I can see marked here, we also have CF congruent to CE. CF is already a side of this triangle, and CE is a whole side of this triangle. So now I have a pair of congruent sides I can use. Whenever we have overlapping triangles, remember there's always something in common, something where they overlap. It's either a shared side or a shared angle. So when you separate the triangles, it's easy to see what's shared because you can look out for the letters that are the same. If there's two letters that are the same, well, that means that you have a side in common because line segments have two letters. If you see just one letter in common, that means it's a shared angle. And looking at these two triangles, the only letter that I see as the same is letter C. So we have a shared angle here. We have angle C congruent to angle C. And if I take a look at the original diagram, notice how both of the triangles do overlap at angle C. So we have angle C congruent to itself by the reflective property. And as you guys can see now, the two overlapping triangles are congruent by angle side angle, angle side angle, ASA. And once we know the triangles are congruent to each other, using CPCTC, I can say, well, if the triangles are congruent by CPCTC, corresponding sides BC and CD also need to be congruent. And that's the two sides that we wanted from the beginning, the two consecutive sides that we started with a little bit of information about. Now that we know consecutive sides of this parallelogram are congruent, we for sure know that we have a rhombus. And that's the last step of my proof over here. ABCD is a rhombus because a parallelogram with two congruent consecutive sides is a rhombus. So keep in mind when you're approaching any proof question, after you take a look at your givens and mark your diagram with what you can, take a look at what your goal is. And just like we did here, try to narrow down what property you're going to be using to prove that you have a specific quadrilateral. Here, Since we didn't have any diagonals to work with, and 2 of our special rhombus properties involve diagonals, it was pretty easy here to narrow down that we were going to be showing that sides were congruent to each other to prove that we had the rhombus. And then we just needed to figure out how to do that. But if you know what property you're going to be using, that's at least a start. And then whenever you have quadrilateral proofs, always look for triangles inside those quadrilaterals. And once we figured out that we needed sides of the parallelogram to prove it was a rhombus, it was pretty easy to figure out which triangles had the sides that we were interested in as sides of those triangles. Overlapping triangles come up a lot. Make sure to draw them separately. It takes 2 seconds to draw them separately, and it makes it a whole lot clearer what is going on in those triangles. Otherwise, a lot of people identified that they were working with these 2 triangles, and they didn't realize that CF and CE were actually sides of those triangles, and they were trying to use addition once again to make the sides bigger when they did not have to. Moving on. Okay, so once again, I have the proof here because I wrote it up in the last video, but we're going to remark the diagram and go through the proof together so that we can talk about some things as well. So in our givens, our first given is that ABCD is a square. Now, there's a lot of things we know about squares because they have all the properties of parallelograms, rhombuses, and rectangles. That's like 50 million things we know about them. So I'm going to hold off on marking all the square properties I remember until I mark the rest of the given information and take a look at my goal. And then I can figure out what's going to be important to me like we did in the previous proof. So we're also told that we have segment BAE, I see that here, segment DAF, I see that here, and we're told that AE is congruent to AF. Gonna mark that. And our goal for our first part of the proof is to prove that triangle BAF is congruent to triangle DAE. So looking at these 2 triangles from our given, we already had a pair of congruent sides. I also see vertical angles. Vertical angles are really nice because they jump out at us. They're formed by intersecting lines. They come out of the same point, and they look like they are opposite from each other. Sorry, it's really hard to write on the computer. So we have our vertical angles, angle BAF and angle DAE. And vertical angles are always congruent. So now I have a side and an angle right next to it. It would be really nice if I had the side next to that on each of the triangles, because then I would know the triangles are congruent by side, angle, side. And guess what? We do know. Oops. We do know that these sides are congruent. The reason why is because we knew that ABCD was a square. And squares have 4 congruent sides. All the sides of a square are congruent, so we do know that. So now we've already accomplished our goal for part A with just 1 square property and vertical angles. We now have shown that the triangles are congruent by side, angle, side. The second part of the proof is to show that angle CBF is congruent to angle CDE. So angle CBF is that whole angle there. I want you to notice that this angle is not inside the triangle. It's not inside the square. It combines the square angle and the triangle angle. So it's bigger than the square angle. It's bigger than the triangle angle. It's both. Angle CDE is right over here. And once again, it is bigger than the triangle angle. It is bigger than the square angle. It combines both, the angle from the square and the angle from the triangle. So you might be thinking, that sounds like addition. If I can add the angle from the triangle with the angle with the square, and over here the same thing, the angle from the triangle with the angle with the square, I can make those whole bigger angles that I'm interested in. That's a great idea, and we can definitely do that. But remember, to use addition, we do need to be starting with congruent pieces and adding congruent pieces. So we are going to have to state that the triangle angles that we want are congruent, and that the square angles that we want are congruent? Well, in part A, we already proved these two triangles congruent. So we can definitely say that angle FBE and angle ADE are congruent by CPCTC. They're corresponding angles from those two congruent triangles. And we can definitely say, let me just use a different color for this. We can definitely say the angle CBA is congruent to angle CDA. And the reason for that is because a square has all equal angles. Remember, they're all actually right angles because it's a property of a rectangle that all the angles are congruent right angles. So squares have it as well. All four angles of a square are congruent right angles. So angle CBA is congruent to angle CDA because all angles of a square are congruent. Now that we know the pieces are congruent, we can add them together to make angle CBF and angle CD. And you can see that in my proof over here. Steps 1 through 4 are for part A, showing that we have the triangles congruent with side angle side. In step 5, I say that the two angles that we need for the addition in the triangles are congruent by CPCTC. In step 6, I mention that the angles from the square that we need for the addition are congruent, and that's because all angles of a square are congruent. In step 7, I add the parts of each of the angles together. And in step 8, we arrive at our goal through substitution. The last piece here is the extra credit. So, let me undo this all so I can redo it again. Let me pause the video so I can get rid of all these lines. Okay, so this is a two-part extra credit question. So it said to construct a right triangle, and then once you had your right triangle, to construct a midsegment of that triangle. So here I have a line segment. I'm just starting off with any line segment. Let's get rid of everything else that's still there. Okay, so I'm just starting off with a line segment. And the easiest way to construct a right triangle is, if you have a line segment, is to construct a perpendicular bisector of that line segment, and that will get you the right angle that you need for the right triangle. It doesn't say like if it needs to be equilateral, isosceles, or scalene, so the side lines don't matter. The only thing that the question is asking you for here is to make a right triangle, so we just need to guarantee that it has a right angle in it. So I'm going to just perpendicular bisect my line segment. Let me just use the same color for this one. Okay, so I'm going to open up more than halfway down. Doesn't matter the exact arc above and below. Then I'm going to move on over to the other endpoint without changing the distance on my compass. And same arc, using my straight edge. I'm going to connect. Oops, I did not connect that good. There we go. It's hard to connect it on the computer. And what I have here now, since this is a perpendicular bisector of the original line segment, we have made a 90-degree angle. So since the side lines don't matter in this question, it just asked for a right triangle, I'm just going to connect down and draw a hypotenuse to make a right triangle. So now I have a right triangle. The next part is to just construct a midsegment of the triangle. So in order to construct a midsegment, I need midpoints of two of the sides, and then I'll connect the midpoints together. Best way to get the midpoint of a line segment is perpendicular bisector, just what we did just now. So I'm going to use a different color for this so all my arcs don't get confused. So let me switch my color. Okay. So I'm going to do this side, I guess, and this side. So I'm going to start with this side over here, this leg of my right triangle. So I'm going to go over to one of the endpoints, and I'm just going to open up more than halfway. The exact length doesn't matter. Arc above, arc below, heading on over to the other endpoint of that side. Same arc above and below. Now let me get my straight edge, and let me use purple as well to be consistent. And I'm just going to connect from endpoint to endpoint here. And I'm doing that as best as possible because it's really hard on the computer. The part where my perpendicular bisector, that point where it hits the triangle, that would be the midpoint of that side of the triangle. So I have one midpoint. I just need to find the midpoint of another side to make the midsegment. So let me use a different color for this. And I'm just going to go over to the endpoint of the other side I'm using. More than halfway down, but the exact length doesn't matter. Arc above and below. Using the same distance. Heading on over to the other endpoint. Arc above and below. And let me get a different color for my line. And using my straight edge, I'm going to connect from intersection point to intersection point. And that spot where the perpendicular bisector hits the side of the triangle is the midsegment of that triangle. So now all I need to do is the midpoint of that side of the triangle. So now to make the midsegment, all I need to do is connect midpoint to midpoint. So that yellow line that I just drew connecting midpoint to midpoint is the midsegment of this triangle. So it's just annoying, a lot of perpendicular bisectors to get midpoints. But once you have the midpoints, you just connect them together.